Hi, so welcome to the video. In this video I would like to talk about particle sizes and especially about how to determine the size of single particles. Therefore, I have the following plan for this video, and this is I would first like to introduce the question why particle sizes are so important. Then I would like to give you the knowledge about how to describe particle sizes by statistical numbers. You will get an insight into digital analysis, how do we use digital tools, and finally you should also understand the concept of equivalent diameters. But to start, I would start a little bit more generalistic, and this is by the property function from Hans Rumpf, a very famous professor in particle technology. And the idea of this property function is that you have product properties and they are related to the physical characteristics of particles. And the question is, how are they related? And to give you some examples, so we have product properties like the color of a product, the taste of a product, the agglomeration behavior of a product. You may be wondering, but if you think about coffee, about cacao. So you put cacao as powder into milk, how does it dissolve, right? That agglomeration behavior is very important. And some others, and on the other hand, you have the physical characteristics of the particle size, of the particles, and these could be size, shape, density, and so on. And the the property function relates these physical characteristics to these product properties. So by adjusting the size, you can determine the color. And what you have to realize, and there's a very nice quotation in a book, and this is all particle properties depend on their size, some vary. So at the end, all of what you see here has to do with the size of the particles. And there I would like to give you 3 examples, and one is what you see here. This is coffee versus espresso. I really like to drink coffee, and I actually have a coffee here right away. And what you see is different type of coffees, different products, and the size of the coffee powder. So you take the coffee bean, you grind it, and if you make very fine powders, you can make a Turkish coffee on espresso, while with larger powders, you get a different product, a filter coffee or a French pressed coffee, right? And here you see images from our lab. So we took some coffee beans and grind them with this very nice mill. And we have larger particles here and smaller particles here, as you can see. And the larger particles gives a nice Americano, and the smaller one gives these espresso. But you also see that it's not so easy to distinguish them because they have already different sizes. But we see here are quite larger, here are a few smaller. So a second example would be this. This is the compressive strength of concrete. So concrete, and I have one here, is a present from one of my students. She made it as a present when she finished her job with me. And concrete consists cement. And cement particles are measured here by size, and you see a size distribution. So this is the particle size. And here we have a quite large size with a broad size distribution, so ranging from 5 to 100. And here we have very small cement particles with a much narrow size distribution, so only ranging from 3 to 20. And if you put them now and make these kind of blocks, which you basically do in the lab to test, you see a clear difference in property in terms of compressive strength. So small particles with a narrow distribution give very strong concrete. Large cement particles does not give such a strong concrete. And the third example you see here, and these are microplastic we are investigating. And microplastic comes mainly from textiles. And when you put the textile into the washing machine, the microplastic is washed out, and you don't want this. This is one product property. And on the other hand, you want to filter it. And to filter it, you need to understand, and you see these rods here, right? These are really microplastic particles which we need to filter out of the water. Okay, so with these 3 examples, I hope you get an idea that particle size is a really important measure. And how do we measure it? So you put a particle in a microscope, as you see here, and then you watch from the left. So this is the particle, and you watch from here. And then you can measure different statistical measures, basically. So you can measure the ferrite diameter. And the ferrite diameter is this line here. So I'm looking from here, so the vertical projection in measurement direction. Then we have also the Martin diameter, and this is the length of the line halving the projection area. So we have it here, right? Halving the projection area in the middle. And then we have the longest line through particle projection parallel to measurement direction. These two are not so often used. The farad diameter is really often used, and I would like to show it on this example. So this is sand, very simple particles. And now you put them in the microscope, and the question is, okay, how do we measure the size now, right? Because they have these weird shapes, and here we have the scale. And now we can make use of farad diameter and so on to measure it reproducible, right? And what we do is we make these images in the microscope, and then we have to process it, and you can do this with tools like ImageJ or Python. And the first is you take the image and you change it to an 8-bit. So you don't really see it here, but this is an 8-bit version out of this, so it's just a smaller, easier picture. And with this you can further make your analysis, and then you make a black and white picture, as you see here, right? So you just simplify the image, and now the computer can very easily identify the particles and determine their sizes. The software is very powerful because it does all of this for you, and also it could be that you, for example, have dust in your particles, or you want to exclude some sizes, and as you see here are numbers, so you can set a threshold size exclusion. Min and max values can be set for the particles you want to look at, and in this way you only get the yellow marked ones, and all these small dust one, which is really not part of your particles, are not considered. And the second one is the so-called water sheet separation. So you have two particles touching each other, but based on the deepness, the shape, the sharpness of the picture, the computer realizes here is a border, they are touching. And in the large particle, you lose a lot because he fakely identifies here areas, but the particles on the edges are not counted. But this one he finds quite good, and you lose only a very small part here. So basically you are able to identify this particle, and this you will anyway not measure because it's on the border. So two ways how the software can be very, very helpful. And basically once you did it, you get here all these numbers you can get. You can get the circularity, which is the shape, the roundness, and so on. And you see that you have also the max, the min farad diameter, and you also have the ratio of the farad diameters. So the farad diameter basically is the number you measure out from these optical analyses. Good, but there are also some other ways, and these are called equivalent diameters. And the equivalent diameters have now a D. If you remember, in the farad diameter we had the X. The Martin diameter has the X, and now we have the diameter in D. So X means we don't know the shape, right? We don't assume a shape, and these particles have really different shapes. And this is not so important to determine the farad diameter. But here we assume, and this is the idea of equivalent diameters, we assume that our particles are spheres. And the sphere has a diameter d, right? We can calculate it, p divided by 6, d to the power 3. And what we can measure is, we can measure the Stokes diameter. So the diameter of a sphere having the same settling velocity in Stokes reading. So this means I take my particle and I measure how fast it settles. Quite heavy stone here, so settles very fast. And there will be a sphere with a given size, which has same density and which has the same velocity. And this sphere is what I determine, the size of this sphere. So I have the size of a sphere having the same settling velocity as my stone. And this is the equivalent Stokes diameter. I can do the same for the aerodynamic diameter. So this is the diameter of a sphere, same settling velocity, but density of 1 gram. Why 1 gram? So this is basically 1 gram is water, and this is very often used for aerosols. Aerosols very often consists out of droplets, of water droplets, So aerodynamic diameter is extremely important for movement of aerosol particles. Then we have the mobility diameter, the diameter of a sphere having the same electric mobility. So I charge my particle and I send it through an electric field, and it will move in the electric field because it's charged. And there will be a sphere, same density, same charged, which has the same speed, same mobility. That will be the equivalent diameter. And at the end, very important, the optical diameter. The optical diameter is a sphere having the same scattered light behavior. This is a very often used measurement technique to determine the size of small particles. So I have a light, and the light is scattered by my particle, and there will be a sphere having the same scattering behavior, and this is my optical diameter. Good. So there is another very important measure, and this is the specific surface area. The specific surface area is so important because the surface of a bed of particles is very reliable to measure. So you have a lot of devices which can measure the surface of your powder. You put them where you measure the surface area, and with the surface area you can calculate the size. So what you get is the specific surface area. The specific surface area is here the volume specific surface area, is the surface of a sphere divided by the volume of the sphere, right? And this means a small sphere has a large specific surface area, and a large sphere has a small specific surface area. And if we put the numbers in here, you also see this dependency. So surface area of a sphere is pi times d squared divided pi 6 d cubed. So if you make a little bit the math, you end up with 6 divided by d. So large diameter, small specific surface area, small particle, small diameter, large specific surface area, okay? And we can do the same with the mass. So considering the density would leads to the mass specific surface area, then we just have this divided by the density, and this would add a density term to this here. And with this we can calculate the so-called Sauter diameter. The Sauter diameter, knowing the mass or volume specific surface area of the bed of particles, you can calculate the Sauter diameter d32. Why d32? Because if you look back, 3, 2, volume to surface. This is 3, 2. And this is the equation for the Sauter diameter. And the assumption behind the Sauter diameter is that you can take a powder, put it somewhere, measure the specific surface area, and from this you can calculate the diameter of each sphere, but you consider monodisperse spheres. So this means all of the spheres in your sample have the same size. Okay, with this I would like to end the lecture, and to end the lecture I would like to give you a small exercise that you can train the knowledge. The first one is make or look for a picture with particles and make a size analysis for yourself. You also could use the one from this video, but in the internet you will find a lot, and even in the real world you will find even more, and try to go along the way how I explained it to make these analyses. Then you should try to explain the differences for multiple equivalent diameter for yourself. So you got to know different equivalent diameters, try to reproduce them and tell yourself what is the difference. And at the end you can also make a small calculation. So using BET measurement, which is a very nice device we have in our lab, you calculated specific surface area of 0.1 square meter per gram and 10 square meter per gram for iron oxide catalyst particles. And the question is, can you determine the size of the investigated particles? So the size of this sample, the size of this sample, all of them are iron oxide particles. Good. To sum up, I hope you get an idea why particle sizes are so important, why it's interesting to work with particle sizes, that you get an idea and how you can describe the particle sizes by statistical numbers, right? Ferrite diameter and so on. You know how to use digital analysis to get these numbers, and at the end you understood the concept of equivalent diameters. So with this, I would like to thank you to watch the video, and if you have any questions, please yeah, just ask me.